So good afternoon everyone, this is Arun Sharma from Midas, welcoming you all to the session 4th of Midas Elite Center course. Today we will be covering soil structure interaction analysis for shored excavations. And Midas holds the rights to the material that are shared in this presentation. So without our consent, please don't share or reproduce any material of this presentation. So these are the learning objectives for today's session. At the end of this course, participants will be able to understand the key advantages of utilizing numerical analysis for shored excavation. They will also be able to understand the comparison with conventional design process and the conditions that necessitate the 3D analysis for shored excavation. So this course is divided into 4 chapters. Chapter 1 will talk about the background of deep excavations, what are the different types of supporting systems, and what is the design process for each one of them. And the second chapter will deal with the approaches of shored excavation design. So what are the earth pressure, how they are computed, what are the supporting systems, how we choose which supporting system is relevant for what kind of excavation. Then in the third chapter we'll talk about how to use numerical analysis, and more importantly we'll be focusing on how to choose an appropriate constitutive material model, how to simulate the supporting system, and how they compare with the conventional approach. And in the end, the fourth chapter will cover a case study of high-rise building foundation design that required deep excavation and complex supporting system. So let's start with chapter 1, which is the deep excavation. So as we all know, the definition of deep excavation is something like this: the removal of soil to construct a foundation and underground structure is called excavation. Now, depending upon to what depth and dimensions you excavate, you deal with either deep excavation or a shallow excavation. Usually for building foundations and underground structures, we have to go deeper into the earth, and therefore every time we are doing an excavation for a building structure or foundation of a building structure or underground storage structure, you are dealing with deep excavations. So let's see what are the different types of shored excavation systems available. So for shallow trenches, which are primarily used for laying down the pipelines or sewer lines at near ground level, or utilities lines. So for this, usually the trenches are shallow and are pretty narrow also. So we have these kinds of shallow trenches supports that are applied at close intervals. Then we are all familiar with sheet pile, which is very thick corrugated metal plate which is tied with each other in the transverse direction to form a wall. So this is called a sheet pile. And in these couple of slides that will be following, we'll be talking about what are the different types of shoring systems. I'll not be talking about where they are used and why. That is something we'll be discussing in the following chapters. Then we have soldier and legging supporting system, where we have vertical steel pile members that are drilled into the ground, and we have timber or concrete laggings in the transverse direction to provide the support to the excavation. Then another way of supporting the excavation or the wall is soil nailing, where we use long rebars or iron nails to hold the slope in place, and this type of method is useful depending upon the slope of the system. Another method of supporting the excavation is through bracings, like excavation bracings, which are usually used at closed excavation sites. And if you are dealing with open systems, then you can use tiebacks, where we tie the walls through the walls to the excavation slope itself. So now let's move on to the design process of these excavation supporting systems. So I'll go through the steps that are involved in the design process one by one, starting with the first step, where we have to select the type of lateral earth pressure that are expected to act on the wall. So usually, as we know, there are three types of lateral earth pressures: earth pressure at active, at rest, and passive. So here you can see the directions where these earth pressures are acting. If this is our supporting system, then behind the supporting system, the earth pressure is considered active. In front, it's passive, and at rest is the earth pressure, which is at a stable strata far away from the actual excavation edge. But some points are to be considered while assessing these pressures. The first point is that most commonly used earth pressures are active and at rest. Then you must consider water pressure at poor drainage sites. So if we don't have a good drainage system at the site, you can assume a huge poor water pressure due to the soil water inside or retained by the soil that can cause additional or increased earth pressure onto the supporting system. And depending upon the codes that you are using, or depending upon the country you are in, you might be required to multiply this factor of safety to the pressure itself to before assessing the design needs. Now let's move on to the step 2, which is to apply external stability checks to ensure the overall stability of the shoring system. So let's see what are the external stability checks. The first one is the passive resistance of shoring system, which is actually the factor of safety against sliding. And as you can see, the empirical formula is pretty straightforward: resisting horizontal forces divided by driving horizontal forces. And the minimum factor of safety required for this stability check is 1.2. Then we have to ensure the safety against overturning with a factor of safety of minimum 1.5. And as you can see, the formula, it is pretty simple, straightforward. It's a ratio of resisting moments to the driving moments. Then let's move on to the third step, where we have to determine the bearing stability of the shoring wall. Now, if this is our retaining wall or the supporting system here, we must check the bearing stability of the soil on which this wall is constructed. It is critical if your wall is based on soil and not on stable rock strata. And the bearing stresses should be checked for both heel as well as toe, because if the system is mobilized and it goes for an overturning failure, then the stresses at the toe would increase and the heel would reduce. So we have to consider the bearing stresses at both locations. Then the bearing stresses are checked against the permissible bearing stresses of the soil, and the minimum factor of safety should be 3. So if you are able to get this check and the factor of safety is 3 or greater than that, then you don't need to consider any settlement control. But if not, then you have to take measures for assessing the settlement that will be occurring underneath the wall, and if there are certain measures to control it. Then the fourth step is to check against global failure. Now, if you look at this diagram here, we talked about the factor of safety against overturning, against sliding, and these are all external factors. But the factors that are beyond our control are actually the settlement of the soil underneath the wall itself and the complete failure of the soil slope. So if the failure occurs something like this, which sweeps out the entire failure surface, then you can't really do anything about it by assessing the factor of safety. So how you can ensure this safety against global failure? So for this type of failure, as we know, is caused due to the soil below the retaining wall, and if you are working on sites which have weak soil strata, or you are working on hillsides, this check is essential. So for this check, you must perform a numerical analysis on these sites. So once you identify that you are working at one of these sensitive sites with poor ground conditions, it automatically calls for a numerical analysis to assess whether the soil or the slope will fail, causing the global failure of the supporting system. And the fifth and the last step for design process is to check the shoring system for its structural stability. So here we need to, it is necessary to check the individual components of your shoring system. If you're working with wall, if you're working with nails, if you're working with tiebacks, if you're working with bracings, you must compute the section size, reinforcement if you're dealing with reinforced concrete, and the length of the members that are needed to give the structural stability to your shoring system. And in order to design these shoring components optimally, you must have accurate design forces. And this is a very big component of the entire design process. If you don't have accurate forces, you will always end up with oversafe structures, and which will be which will not be cost effective. And you'll see later on in the following chapters, when the size of the structure increases because you are dealing with deep excavations, then cost of the structure, the time of the construction is a sensitive issue, and that creates a big difference on your bids. So for deep excavations, these parameters are more important as compared to the shallow trenches or shallow excavations. So this brings us to the end of chapter 1. Let me quickly summarize the points we learned here. So deep excavation means removal of soil for foundation and underground structure. Different types of shoring systems are available, like shallow trenches, excavation bracings, tiebacks, sheet piles, soil nails, soldier piles and lagging. And different shoring systems are used based on different site requirements. The design process of the shoring system includes: step 1, governing lateral pressure determination, which is usually active or at rest earth pressure. Then external stability against sliding must be checked with a factor of safety of 1.2, and overturning stability should be checked with a minimum factor of safety as 1.5. The bearings stability check is critical for poor soil. The minimum factor of safety should be 3, otherwise settlement control might be needed. Global failure check at hillside and soft grounds and unstable strata is needed, so for which you need to perform numerical analysis. And the structural design of each component with accurate design forces is very, very essential. So now we'll move on to our first quiz, which will have 3 questions. The duration will be 5 minutes. The questions are multiple choice. Chapter. Where we will be talking about the different approaches for shore excavation design. So we'll start with the uh, earth pressure discussion. So the basic concept of earth pressure is pretty simple and straightforward, as we all know. This is our retaining structure or supporting system where we have earth on either side. Obviously, since we have excavated on this side, there will be earth at a higher height behind this retaining structure or supporting system, and due to the height here, we'll have earth pressure actively acting on the wall to cause its failure. So therefore, this pressure on the wall towards the earth is called active earth pressure, and the formula is pretty simple, straightforward, as you can see, where Ka is the earth pressure active earth pressure coefficient. Then there is earth pressure at rest, which is actually acting at some way away from the wall at a stable condition, and the earth pressure is actually directly proportional to the height at which we are talking from the top. So basically, this earth pressure is K naught times the height times the density, and the K naught is actually a coefficient which is computed based on the internal angle of friction, and you can see the formulation for non-consolidated soil strata and for consolidated or over-consolidated soil strata. I'll not go into the details of these equations. These are something we all know and have read during our geotechnical courses 101 or soil mechanics 101. And then we have the passive earth pressure, which is on the other side of the supporting structure, which is here, and it is also active. Sometimes this pressure could be critical, but majority of the time we always go for active earth pressure or earth pressure at rest. Then the apparent earth pressure diagram that were proposed by Tergazi and Peck in 1967 and 1969, we found that for the supporting structure, depending upon the soil strata, the pressure definition is different. Depending upon the soil strata, as you can see, if this is the height H and these are the intermediate, let's say, bracings or supporting systems, then the pressure is more or less constant throughout the depth, and the coefficient of earth pressure is determined based on this formula. Whereas if you are working with stiff or fissured clay, the variation is somewhat different. You see a triangular tapering for the first quarter of the height, then the second half is constant, and then the third quarter of the or the last quarter, I should say, is varying again, and the pressure variation is from 0.2 to 0.4 times density times height. Then if you are talking about soft to medium clays, then it is a different variation altogether. You see for the first quarter the pressure varies, and then it stabilizes for the rest of the depth of the soil strata. So two things we can observe from here, that soil pressure definitely varies depending upon the soil type you are using, and it definitely varies with the depth of the excavation. And if the depth of the excavation is very deep, then these variations are different from the realistic behavior. We'll talk about that in a short while. So as we saw, the earth pressure varies with height depending upon the soil type. These formulas and theory work brilliantly for shallow excavations. But for deep excavations, as the depth goes on increasing, the variation of earth pressure is larger as compared to the conventional methods that we just saw in the previous slide. So therefore, the estimation of earth pressure becomes critical, and for deep excavations, engineers prefer using numerical analysis. So this is the first time we are introducing you to numerical analysis, and you must understand that earth pressure is a critical component of the entire design process. So let us see how the two methods are different. Method 1 is the conventional method that we have been using all this time. So the biggest difference between conventional method and numerical analysis method is the application of the earth pressure. So under conventional method, the earth pressure is basically an input parameter. Engineer has to calculate the earth pressure depending upon the formula you just saw in the previous slide, and then apply that earth pressure to the wall, and we are basically doing the structural stability design of the supporting system based on that earth pressure. This method has been used very extensively and for a really long time, and it works brilliantly, like I said, for shallow foundations or shallow excavations. But let's see what is numerical analysis all about. So numerical analysis, the earth pressure is actually the output result. So this is from after the numerical analysis you will obtain earth pressure, whereas in conventional method you input earth pressure. So engineer has to create mesh for ground as well as for the wall, and then assign a constitutive material model for the soil, and the stress and strains are calculated based on constitutive model and external loads that are applied. And after analysis, engineer can obtain stresses or earth pressure for each direction. So you must be wondering why we have to do numerical analysis when we can easily compute the earth pressure from the previously discussed formula. It's because when our height of or the depth of excavation increases, these formulas and the variations that they propose are no longer valid, and therefore if you are dealing with deep excavations, you must use numerical analysis. Otherwise, your cost of construction, cost of material, time, everything will go beyond proportion, and you will end up with a either a very oversafe design, which is economically not viable, or you will be at risk with different adjacent structures stability. Now let's briefly talk about the selection of different supporting systems. So first thing that we should bear in mind is that there is no one size fits all solution for the excavation supporting systems. And the second important point is that the first step to read is to read the plans, specifications, geotechnical reports to understand the constraints and the conditions that will be encountered. As I discussed in the previous chapter, that there are different types of supporting systems and they depend upon the site specifications. So this point is reinforcing what we just discussed. Then let's talk about shallow trenches. There are temporary support methods such as trench boxes, shoring bracing system, or hydraulic shoring systems can be utilized for the support. I am getting some comments from our users, so sorry, from our attendees. So I'll be going over these questions in a little while because I have moved on with the session. So once we are at towards the end of the session open for discussion, then I'll be taking up those points. But don't hesitate to keep your questions till the end. Keep sending it to us and we'll be going over them towards the end of the session. Thank you. Now resuming the presentation here. So let's talk about trench boxes, where we should use trench boxes and where other types of supporting systems are sufficient. So trench boxes are basically used when you have to get your workers down in the trench to set things up, such as laying of pipelines or utility lines or some fixtures that you have to apply. So the trench boxes basically support the walls as well as the soil to fail and cause cave-ins and prevent accidents. But if you don't have to get the workers in the trench, then most of the time the shallow trenches bracing systems are used. And for utility trench excavations, cross trench bracings is used. But cross trench bracing, as we all know, it's somewhat restricts the work area. So if the need is to get someone in the utility trench and work, it is recommended to go for box trench because safety is the most important thing. But if it is something that could be managed from outside the trench itself, then cross trench bracing is the next best option. Now that was for shallow trenches. Now let's move on to the deep cuts. So the excavation depths that are exceeding 10 to 20 feet require specialized planning for supports. Like I mentioned, all the support systems depend upon the site conditions and soil conditions and the dimensions of the excavation. Deeper you go, more material you need, so you have to optimize your support conditions so that you don't cause any stability risk to your existing structure as well as adjacent structure. So these should be dealt with caution. So the support systems that are popularly used for deep cuts include soldier pile and lagging, soil nails, excavation bracings, and tiebacks. So we'll cover each one of them very briefly. So the soldier piles and lagging method is very commonly used, and but if you are dealing with sites which are having soil layers that are completely cohesionless, let's say sand strata, then this type of support system should be avoided. But if you can't avoid, and that is a constraint that you have to deal with, then soil sheeting is to be applied on the surface of the laggings in order to get the cohesion resistance going along with the laggings. I hope this explanation is clear. Then the next method, and very popular method, is soil nailing, which is a rapid, economical, and the least disruptive means of constructing excavation support systems. But it requires an unusual amount of handwork, craftsmanship, and geotechnical knowledge to construct these type of supporting system. For narrow excavations, excavation bracings with internal struts are most appropriate because they are narrow in nature and they are deep. You can't really go in and do soil nailing, so it is better to have internal struts to provide the required support. Then another way of providing the support, and a very popular one, is anchors or tiebacks. Now the advantage of using anchors and tiebacks is that they eliminate any kind of obstruction in the excavation, and if you are applying struts to open excavation sites, then you are actually limiting your work scope and causing obstruction. So if you are dealing with open or closed excavation sites and you can do with without struts, I would say it is better to go with tiebacks. And tieback systems are generally very successful in preventing the movement of the excavation walls. Now this brings us to the end of chapter 2. So let me quickly summarize what we learned in this chapter. So calculation of earth pressure varies based on soil type and Tergazzi's and PEC formula that are commonly used. Design of shoring system as per conventional method involves earth pressure as an input parameter that is calculated based on the prevalent formula. Design of shoring system as per numerical analysis uses constitutive material models as per soil conditions and gives earth pressure as an output for structural design or check of the shoring system. Numerical analysis is must for deep excavation. And support selection depends upon soil type, dimensions, and purpose of excavation, whether it is a utility or non-utility excavation. Shallow trenches usually use trench boxes where workers need protection against cave-ins. Otherwise, cross-trench bracings would suffice. And deep excavation exceeding 10 to 20 feet require specialized planning for support needing numerical analysis. And finally, tiebacks eliminate obstruction and prevent wall movement, while strut should be used only for narrow excavation where tiebacks can be installed. I hope the explanation was useful, and now we are so I see everyone has submitted the quiz, so let's move on. So let's move on to the chapter number 3, that how to use numerical analysis for performing the deep excavation supporting system design. Let's start with the constitutive material model. As you can see from this slide, there are different types of material models and they are used for different to simulate different behavior depending upon the soil. So as you can see, we have linear elastic behavior, transversely isotropic, then we have Drucker-Prager, we have Moore-Coulomb, we have modified Moore-Coulomb, which is actually for elastoplastic and cap hardening behavior. Then we have Hook and Brown, which is for elastoplastic. We have hyperbolic for nonlinear elastic, etc., etc. Now, as you can see from this slide, we have highlighted or used bold for Moore-Coulomb and modified Moore-Coulomb. This automatically goes to show that these are the two main material models or the constitutive material models that we most often use. and out of these two, Mohr Coulomb is the more popular one, and we use Mohr Coulomb more often than a modified Mohr Coulomb or advanced constitutive material model. So I'll go into the definition of these models, what are the parameters and why they are used. So as you can see here, for the application of Mohr Coulomb and advanced models, so I will refer to modified Mohr Coulomb as advanced models or hardening model so that there is less confusion. So for shear soil failure, soil shear failure, we use Mohr Coulomb model, and we also use equivalent linear stiffness for compaction or unloading behavior. So Mohr Coulomb model alone doesn't suffice. It also requires an equivalent linear stiffness for the compaction and unloading behavior when you are dealing with excavations. But if you are looking to simulate a nonlinear compaction or shear failure analysis, then we use advanced models such as hardening model or modified Mohr Coulomb. And as you can see, there are various types of field tests that are conducted and theories based on which the parameters are obtained for Mohr Coulomb model. So let's see the applications of Mohr Coulomb model. So Mohr Coulomb model is generally sufficient to model the stability analysis for slopes, embankments, abutments, for ultimate load analysis for bearing capacity problems, punching shear, for soil structure bond failure, for ground anchors, soil nails, geotextiles, for excavation problems with basic behavior. So this is something to be noted. For most routine excavation problems where you are interested in the basic behavior of the soil and the soil structure interaction, Mohr Coulomb is sufficient. So let's see why and where do we need the advanced models. So advanced models are required if you have to do a detailed analysis such as a settlement analysis of foundation and embankment on soft soil. For this you would have to consider undrained or over consolidated silts and clay stratas. You would have to deal with the consolidation of soft soils. And the another area where these advanced models are required if you want to do a detailed analysis of deep excavation with detailed behavior. So the difference for us for this particular session, since we are looking at a very objectively deep excavations, I would say if you have to do a basic analysis or a basic behavior representation of excavation, Mohr Coulomb would be sufficient. But if you are dealing with soil stratas which are complex and are considered to be soft soil or can undergo decent amount of consolidation, then you would need the advanced models. So here you can see there are different stiffness parameters for the advanced constitutive model. So I'll not go into all these details, but I'll just briefly mention some points that are of relevance to most of the geotechnical engineers. So there are different types of modulus of elasticity for soil, or Young's modulus, and as you can see they are denoted as E50, EOID and EUR. So E50, as you can see, it's a secant Young's modulus at 50% of shear failure in the triaxial test carried out under reference pressure Pref. So Mohr Coulomb model in itself largely uses E50 as the modulus of elasticity. Then there is EOED, which is actually the tangential odometer modulus at reference pressure. So for this we have to perform odometer test, primary loading, and then we have EUR, which is unloading and reloading Young's modulus. and again at reference pressure. So there are different guidelines when you're dealing with different types of soil types. You should use different type of Young's modulus. So these are all the parameters that you have to throw in advanced constitutive material models. If you're dealing with Mohr Coulomb alone, then largely you would be using E50. Then there are additional parameters that are required to complete the definition of advanced material models, and you can see they are determined based on different types of field tests that are accounted for. So since there are so many tests and so many parameters that you have to account for, so what are the advantages of doing all this as compared to Mohr Coulomb? So the advantages are that advanced material models show better nonlinear formulation of soil behavior in general, and you can use for both soft soils and harder types of soil, whereas Mohr Coulomb goes well with the harder types of soils where there is no significant consolidation or settlement occurring. Then there is a distinction between primary loading and unloading and reloading. So the advanced material models can account for the primary loading that is actually coming from the earth pressure directly, and then unloading because the soil strata is excavated, so there is unloading of the structure. So of the soil strata, so that could cause soil heaving. For that we require a different Young's modulus, that is EUR. So Mohr Coulomb uses just one E50, whereas advanced material models use E50, EUR wherever it is needed. So therefore there is a distinction that you could catch when you are using advanced material model. Then the stress history of pre-consolidation stresses could be accounted for when you are dealing with using advanced material models, and different stiffnesses for different stress paths based on the standard test. This is just what I discussed about the different Young's modulus. And then they are suitable for unloading situation with simultaneous deviatoric loading, which is actually the definition of excavation in terms of numerical analysis. So unloading situations means that you are excavating your earth mass, and as and when you are excavating your earth mass, you are developing the deviatoric loading onto the structure due to the unloading. And this is also essential when you want to do a detailed analysis of deep excavation and unstable soil strata, because as you see, as you go deeper into the earth, you are taking out huge chunk of earth mass, so you are causing a lot of earth load to be removed from the soil strata, so it can result in huge heaving at the base of the excavation sites, which could be very critical. But having said all that about the advanced Mohr Coulomb material model, we still don't use it that often because of its difficulties in catching all these parameters from all different field tests. So therefore, Mohr Coulomb model with correct parameters may give better results than using incorrect parameters from approximate tests with advanced material models. So it's something like it is better to be more aware about what shortcomings you have rather than over assessing the your strengths. So let's see how the material actually behaves in excavation process. So first of all, there is a huge unloading due to excavation, like I just mentioned. Vertical unloading due to removal of the earth mass, at the excavation bottom, and then there is horizontal unloading behind the wall, and that may be accompanied with plastic shear failure. Then we have primary loading due to pre-stressing. So if you are dealing with the tiebacks which are bonded or which are pre-stressed, then there is a primary pre-stressing force that is exerted. Then the modified Mohr-Coulomb method is preferred because of its ability to account for non-linear elastic unloading and reloading, its ability to account for shear plasticity due to horizontal unloading, and stiffness for better prediction of trough settlement. So I can imagine that this was a lot of information in a very short time interval. So what I'm trying to do here is summarize the material behavior that we just discussed in bullet points and very precise notes formation. So Mohr-Coulomb gives unrealistic deformations provided you are working with unstable soil strata. Otherwise, you are good to go with Mohr-Coulomb. Now, why we say it gives unrealistic deformations? Because it uses single E value, which is Young's modulus, and fails to cater the complex materials at various zones. It leads to overestimation over the bottom heave, and sometimes the heave of the soil, sometimes heave of soil occurs behind the wall also. Which is hard to account for, and this is what Mohr-Coulomb does, that if there is an unloading, then it will cause a huge heaving without even realizing that there is a wall to support it directly. Then the soil below the excavation behaves with EUR, that is the Young's modulus for unloading and reloading, and the soil which is behind the wall behaves with the stiffness between EUR and E50, but Mohr-Coulomb uses just E50 for all these locations, and which results in a conservative values. So let's see the advantages of the advanced Mohr-Coulomb. It gives qualitative realistic deformations, soil stiffness for isotropic loading, shearing, and unloading reloading can be catered for automatically in the model. It gives more realistic bottom heave and improved settlement trough behind wall. So like I said, if you have more information, more parameters, more field tests, you can more accurately simulate the soil behavior and account for all these phenomena. Then let's talk about how to put this together and create a numerical model and how to simulate the supporting system. We were talking about how to simulate soil all this time. Now let's move on to the structural component as how to simulate the supporting system. So let's start with anchors and tiebacks because they're very popular. So anchors and tiebacks are designed for axial forces, so they must be modeled as 1D truss members. And there are two types of anchors and tiebacks, bonded and unbonded. So if you can see this image here, let's say this is the soil strata and you have these red lines that depict your anchors or tiebacks. So if you're dealing with bonded tiebacks, you should ensure the nodal connectivity all throughout the length of these 1D truss members, so that the soil mesh is connected to the your tieback mesh. But if you're dealing with unbonded tiebacks, then you should just have the nodal connectivity at the end and then the start of your tieback. You need not divide the member and make sure that the nodes are connected with the soil mesh all throughout. And if they are pre-stressed tiebacks, then pre-stressing forces should be applied in the axial direction onto these tiebacks here. Then if you are simulating soil nails, then they are modeled exactly like tiebacks. They are modeled as truss members, and there is nothing like unbonded or bonded for soil nails, so they are always considered as bonded. So make sure the nodal connectivity is maintained between the soil mesh and the soil nail mesh. Then excavation bracing. So since excavation bracings resist the axial deformations or axial forces, we model them as truss members and not as beam members. And since we are modeling them as truss members and there is actually nothing outside the plane to support it, therefore if you divide this member into a number of smaller pieces or number of smaller members, then this will cause errors in your analysis. Because it's a truss member, it cannot support out of plane bending or deflection, and frankly that is not our interest to determine the bending of the struts. So therefore we are using truss members. So make sure that you don't divide them as you model in the soil nails or tiebacks. Then modeling of walls as in 2D analysis and 3D analysis, they may differ. So for 2D analysis, the soil is modeled as with plane strain members, and the wall is modeled as beam member. Now why we are modeling the wall as beam here is that, and not as truss, because we are interested in the bending moments, we are interested in the axial force, we are interested in the shear force or the shear effects in the wall. So that could be captured with beam member only in 2D analysis. So and make sure, since the wall is connected with the soil strata continuously, make sure the nodal connectivity is maintained. So your beam member should be divided all along the length and connected to the soil strata. And if you are dealing with a 3D excavation problem, then the soil is modeled with solids, and as you can see the plates are modeled, or the wall is modeled with plate elements, and the color of the two meshes are different. So it goes to show that there is a different member, a different member type with different material property with different mesh. But if you look closely at the boundary, you will be able to see that the nodal connectivity is maintained throughout, so that the stresses could be transferred from the soil onto the walls, and they can be resisted. So make sure nodal connectivity is maintained, whether it is 2D analysis or 3D analysis for wall modeling. So now let's compare our conventional approach for using it for deep excavation. That conventionally the excavation support systems are designed based on the structural limit equilibrium that prevents the structural failure of the support wall. And as we saw in the previous chapters, that engineers just determine the earth pressure and apply them onto the structural components of the supporting wall, and this perform the structural design. So this methodology works fine for your shallow excavations, but for deep excavations there are certain problems. Let's see what are the limitations or problems. So these methods generally result in excessive wall deformations and ground movements. These methods are relate ground movement to excavation support system stiffness and basal stability, which are based on plane strain analysis that do not accurately represent the nature of deep excavations. So deep excavation behavior, as we have seen all throughout this presentation, is completely different. We are dealing with the different structural system altogether. So these methods don't accurately represent it. Then there is another major phenomena that occurs with deep foundations, and that is not with the shallow excavations, and that is excessive excavation induced movements. And these movements can cause damage or even possible collapse in the adjacent structures. So we need we have to accurately predict the lateral wall deflections, surface settlement, because these are the important design criteria in the analysis and design of excavation support system. Since everything boils down to the economy of the support system, you must accurately understand what are the forces coming onto it and how optimally you can design it to make it a economical proposition. And direct and quantitative prediction of ground movements are not easy task. So they are not simple, straightforward formulations that you can use from the books and do the design when you're dealing with deep excavations. And therefore, finite element models or numerical analysis are required for a realistic study of the interactions between the soil and the excavation support system. So, to consolidate what we just discussed in the previous slide, I have put them in a tabular format where you can see the comparison of conventional and numerical analysis approach against key points. So the soil behavior, first of all, is simulated by Tarzaghis and PEC formula that were coined in 1967 or 1969. And the Moore-Coulomb model and modified Moore-Coulomb constitutive material models are preferred in numerical analysis approach. And the earth pressure, as we have seen based on formulas, are obtained as an input parameter in the conventional approach. And for the numerical analysis approach, we use constitutive material models, and the output of the analysis is actually the earth pressure that is being exerted on your structural system of the supporting structure. Then excavation sequence has a major impact on the stress history, which cannot be considered under conventional approach, but in numerical analysis you can consider it easily. Then excessive excavation induced movements cannot be considered in under your conventional approach, which can be easily simulated realistically under numerical analysis approach. And settlement of soil related to the support is you cannot it's not possible to account for this kind of relative settlement using conventional approach, because the formulas are not tuned to accommodate these kinds of variations. So and these variations could be monitored easily in your numerical analysis approach, and for that you can apply interface elements along the support height so that you can see the relative settlement that is occurring. And in terms of design, conventional approach leads to a conservative and expensive design. Now I am talking in light with the deep excavations, or referring to deep excavations. I'm not talking about shallow excavation here. So for deep excavation, the design is conservative and expensive, whereas a numerical analysis approach gives optimal forces, so you can do an accurate and economical design. So this brings us to the end of chapter 3, and let's quickly go over the summary, the points that we learned in this chapter. So Moore-Coulomb model is most commonly used constitutive material model for slope stability, bearing capacity calculation, soil structure bond failure, excavation problems with basic behavior. For nonlinear compaction behavior required for settlement analysis on soft soil, and deep excavation for detailed behavior, hardening models such as modified Moore-Coulomb is recommended. Excavation causes soil heaving due to the unloading, which can be captured accurately with modified Moore-Coulomb. Modified Moore-Coulomb can vary the E value, which is the Young's modulus for soil, as per the change in the stresses, while Mohr Coulomb alone uses a single value. Modified Mohr Coulombs requires parameters from different field tests, and thus it is only used if it is a critical project. So it's not a commonly used material model. For bonded tiebacks, soil nails, truss members are connected with soil mesh at all points, and for unbonded tiebacks, nodal connectivity is only at the start and at the end point. So basically for unbonded tiebacks, you don't maintain the nodal connectivity all throughout. Then if you're modeling wall in 2D analysis, then you are modeling them as beam, while in 3D analysis they are modeled as plates, and the nodal connectivity with soil mesh must be ensured in both cases. And the conventional method is not suitable for deep excavation as it doesn't consider soil structure interaction, excessive excavation induced movements, and relative settlement. So therefore, numerical analysis is used which considers the above and gives accurate design force for optimal structural design of your shoring members. I hope the points are duly noted. So this brings us to the last chapter of this session, where we'll be talking about the deep excavation for a high-rise building construction. So this is the case study that we'll be covering today. The building that is being constructed is called Odeon Tower. The designers are Stoltanci Bacchi and Vinci Construction in France. And the details of the site are something like this. The structure would be 170 meters in height, and it has 10 underground parking levels. So basically the requirement for the excavation would be about 130 feet approximately, which is 42 meters. And this project, as you can see from the site itself, is carried out on extremely steep sloping land, and it is very unsymmetric, and you can see the area is highly urbanized and densely populated, and between in the area with the sloping profile or the sloping terrain, they had to construct this building. So it is an unusual project. Like I mentioned, it is a 48 stories in a highly urbanized environment, and this building will be placed right in the center of this community, and it requires the clearing of about a dozen houses in the area, and then they have to cut through the rock slopes, which are considered to be stable enough, but still there is a huge excavation requirement for this particular structure. Once completed, this building would be the tallest building in Monaco and one of the biggest or the tallest buildings in France. We have 70 meters of excavation that is underground, and the total story height is 150. So this is the initial state of the site before demolition. There are dozens of houses that would be demolished in this particular area, and the soil structure is also the soil strata that they were dealing with was also an interesting one. There were different type of soil stratas. Thankfully, there was no water in the area, so therefore drainage or the pore water pressure wasn't a big issue with this size of excavation. And here you can see this is a glimpse of tie anchors being applied, and for this they are using micropiles. So basically the work on this site began in 2009, and the complete structure would be ready in 2014 in July. So it is still under construction, and because of the steepness and the height of the structure, they adopted staggered retaining wall construction so that they can erect the wall and mount the equipments, and then do the excavation further, and then move down in a step formation. So here you can see it will give you a better idea about what is a staggered retaining wall construction. So on the left hand side, if you can see, this is the Berlin Wall that has already been created, and these are the micropiles that have been used as uh, uh, tiebacks, and this is the completed retaining wall site, and you can see the staggered construction or stepped construction so that they can mount the equipments on and carry on the excavation as they proceed. So there were several micropiles used to provide the required anchorage at the top. And the worksite itself is looks very cluttered, and there you can see there are so many equipments in the site. And since it's a very sensitive project, so uh, engineers or designers couldn't take any chances, so they had established all sorts of equipments to ensure the construction of the wall is in plumb. So they had uh, piezometers, they had extensometers, they had inclinometers, they had different targets that they were constantly monitoring uh, for any kind of settlement or movement, and monitoring the creep and shrinkage of the wall. So the site was extremely cluttered, and therefore for once they were doing a certain level of excavation, then they had to move everything and set it up again. So it was a very challenging project site to work on. And when we are talking about these instruments or equipments, they are not miniature tools that like a palm top that could be just kept anywhere on the site. They were full size equipments, and every time the excavation was proceeded, they had to move them and set it up. So the whatever space they had was already being used up by the equipments that were there, and on top of that, the access to this site was made possible only by a one-way street. So a one-way street in such a site, and that too, they had to block the street from 7 p.m. in the night time to 7 a.m. and during that time they have to unload all the material that they would need for that days of activity. All the equipments were brought in during that time, set it up, and then they were not allowed to use the street thereafter. And during that time, they used to focus on the construction. So they had to manage the time very well, otherwise it would blow out of proportion in terms of construction cost. So this is a schematic diagram of the retaining system that was adopted. There was a layer of soft soil, so they had to go for fiberglass anchors also. And then there were staggered retaining walls, as you can see, with micro piles to performing the work of tie-back anchors. And you can see there, so basically here there was a combination of different types of supporting systems: tiebacks, retaining walls, and the strut supports when the excavation was being carried out in the confined area. So there were different equipments and different methods used. So the major constraints of this project site itself was it was in a highly urbanized area. So there were several adjacent structures. So there was the neighborhood was densely populated. There were schools and the other community centers and active areas where the foundations were there, and they cannot afford to disturb the foundation of the adjacent structures. So the excavation sequence must be carried out in a step-by-step process with layers of short height. So basically, what were the objectives for 3D finite element from this for this particular project? So first of all, they wanted to estimate the global displacements, and in particularly at the vicinity of the retaining walls and the surrounding area. They wanted to estimate the settlement or the uplift of the tower under the project loads. They want to appreciate the global behavior of the structure by taking into account the 3D effects like arching effects and the upstream of the walls. They had to validate all different types of ground support systems that they were using, if they are working as expected or not. And then they have to check the overall stability. So basically, all this pointed towards a 3D finite element model because they wanted to achieve the global displacement, settlement, the uplift pressure, the global effects like arching of the upstreams of the walls. Then they have to validate these type of ground supporting systems that they are using, and they have to check for the overall stability. Would the entire slope kind of slide, taking the excavation or the retaining or the supporting structure with it? So that all that pointed towards the 3D finite element analysis or numerical analysis. So let me briefly go over the project details once again. The tower building, the building tower is 160-meter high, 10 levels in basement. Retaining structures include 15-meter of high shoulder micropile walls with 48 micropiles, 20-meter high shoulder pile wall with 22 piles, 50 millimeter thick of deep diaphragm wall, and which are 38 meter in height, and 366 pre-stressed anchors were used. So the 3D model should have all these components modeled precisely at the exact location, and so that they can assess whether these for designing these members, the accurate forces are obtained or not. So some components for the finite element model, how they were how they simulated the real situation. So for soil and rock, we used solid elements. For micropiles and piles, we used beam elements. For a soldier micropile wall, which is a combination of shotcretes and micropiles, we used plate and beam element combination. And similarly for soldier pile wall, we used plate and beam element combination. For diaphragm walls, we used plate elements, and plate elements were also used for simulating slabs. And for anchors, we used embedded truss members. And for free part or unbonded anchors, we disconnected them from the solid mesh, and for fixed anchors or bonded anchors, we connected them to the solid mesh, ensuring the nodal connectivity. These were the soil properties that were used. So these are the name of the 5 different soil layers that were found on those sites. And Mohr-Coulomb model was actually used for simulating the constitutive behavior of these soil layers. So we didn't use modified Mohr-Coulomb at this site because Mohr-Coulomb was sufficient to give the accurate results that were needed. So this is the finite element model, as you can see. So there were some villas, high schools, and other structures in the close vicinity, and this was the ODN excavation that was to be performed, and this is a full-blown finite element model. and you can see the nodal connective being maintained as the excavation is proceeded. And these are the different components of the finite element model. If you pull them out separately, so you can see the slabs here, the diaphragm walls, the surrounding walls created with plate elements. You can see the micropiles and the piles and anchors that were modeled. You can see the diaphragm wall, actually that is the wall that was surrounding it, and the barrettes that were like thick walls continuing from the from the foundation to the top. So all different components were modeled as they were observed, or they were to behave on the site. And then the construction was carried out in different stages. So first stage was the stress field initialization, which is the stable soil strata with no excavation happening just yet. Then we set up the soldier micropile wall. Then we did the excavation and activated the pre-stressed anchors. Then we set up the soldier pile wall, and then we did the excavation and activated the pre-stressing anchors. Then we set up the diaphragm walls, barrettes and buttresses. Then excavated and activated the pre-stressing anchors. So everything went in a step-by-step process, and then we proceed with the excavation and activation of basement levels and the application of the gravitational load on the barrettes. Then the slabs were activated, which were the structural component, and then the service loads were applied on top of them. So once these stages were formulated and thrown into the numerical analysis model, the results were obtained as shown here. So you can see the horizontal displacement of the soil strata when you are doing the excavation. You can see the vertical displacement. You can see the vertical displacements of the walls that were there. You can also see the plastic zones that are happening behind the backfill of the retaining structures. So all the results that were needed could be formulated through numerical analysis model, and all these inputs were thrown in one model, and in one run the results were extracted. For those of you who are curious that what tool was used to simulate this deep excavation problem for the foundation and the construction of the Odeon Tower, so let me share the software name with you. It was Midas Civil, sorry, pardon me, it was Midas GTS that was used for the geotechnical investigation and modeling the full-blown finite element model in 3D to estimate the horizontal, vertical displacements and the forces in the members. So this concludes the session for today, and before we leave, I would like to remind you that the next session that is coming up next week, it's on coupled analysis and seismic design application. It will be on September 18th, and the time will be 3 p.m. Eastern Daylight Time. Thanks a lot for joining in today. This is Arun Sharma from Midas signing off. Have a great day ahead. Thank you.